Okay, so I'm a high-pressure experimentalist trying to understand what happens with the heavy noble gases when you compress them and heat them with planetary materials. One of the reasons we want to do that is because noble gases are very key traces of different processes like Earth planetary formation, Earth formation, degassing of the Earth, formation of the continental crust. So it's really important to know how these elements behave in planetary interiors if we want to properly understand isotopic ratios that we measure and how we interpret them. So just a few examples of why it matters to understand xenon behavior is, well, first of all, the age of the Earth is actually not the age of the Earth, but it's the age of some very early meteorites, as most of you know. That's the initial Patterson paper, lead isotopes. So that's the age of the solar system, and you can relate it to the age of the Earth if you do some relative dating between the Earth and these very old meteorites, which is done by using the extinct iodine 129 xenon isotopes and the plutonium 136 xenon decay. So you're doing that, you can see that the Earth should have formed within 100 million years from the meteorites. So basically the age you find from the meteorites is pretty much the age of the Earth. Yeah? So that's the very historical point of view. It has, of course, the data are now much better, much more precise. But even though Ozima and Podolzek noticed that this, were the first to point out that this 100 million years interval is quite large, because they already knew at the time that the core formed much faster than that, few tens of million years rather than 100 million years. So they thought, well, maybe we got this wrong. And also, that's not only the age of the Earth, but the age of degassing, massive degassing, formation of the secondary atmosphere. Okay, so Ozima knew, like noble gases knew, people knew that there is missing xenon. I'll come to back just in the next slide, but if you consider that actually only 0.1, like only 10% of the initial xenon is left on the Earth, or even much less than that, so we'll come to how come this xenon is gone from the atmosphere. But if you consider that, then you shouldn't consider this as the Earth position in this diagram, but you should consider something much closer to the meteorite position, and this gives you much younger ages. So it goes in the right direction if you consider that most of the xenon is gone from the atmosphere somehow. So how we know that? It's not actually since the 70s that compared to the lighter noble gases, so those are the noble gases strands in different reservoirs compared to the solar wind. So you have chondritic reservoirs, so these very old meteorites. And you have atmospheres, so the Earth atmosphere in blue, the Martian atmosphere in red. And these strands are parallel, except for xenon. So they are parallel because between the chondrites, which were somehow the very first bodies, and then they had some history at the end towards making planets. But so every time you lose volatile elements, but you lose, but it stays parallel, except for xenon. So this king here is the missing xenon, okay? And it's the log scale. So these days it's refined to over 99% of the initial xenon compared to krypton is missing from the atmosphere. And not only it's missing, but it's very heavily fractionated. So there is a very strong depletion in light isotopes. Again, same story for Mars. So Mars and Earth have the same problem. So it's called a paradox because xenon is the heaviest. However, there were still different school of thoughts thinking that xenon, despite its weight, escaped from the atmosphere. So to do that, they proposed that either when the sun was very young, you had very strong UV flux that ionized xenon and that it could escape from the Earth, or that you had lots of ocean worth of water that got dissociated, and the H flux entrained xenon. Okay? However, in both cases, you first need xenon to go all the way up to the higher altitude of the atmosphere. Only then you can ionize it and lift it up. And if you ask atmosphere people, they will tell you, no way. No way you're going to lift xenon all the way up. It's too heavy. So that's the major problem with this scenarios, how to lift up xenon all the way up. Now, it was pointed out very early by Podolzak that xenon might be hidden in the Earth instead. Yeah. So this table, for this table, we kind of looked at the literature. Where could we have some xenon excesses compared to lighter noble gases, either krypton and argon? So basically, look up at these two columns, and every time it's higher than 1, it's xenon excess compared to krypton or argon, compared to krypton here and to argon here. So you do find excesses of argon, of xenon, sorry, in terrestrial samples. So those fluids are fluids from the mantle, and they are enriched in xenon compared to krypton. Not to a vast extent, but the several folds. The same for xenoliths. So xenoliths are mantle rocks that have been brought up to the surface with lavas, yeah, quite fast. They do have xenon excesses. And much more important excesses are reported in continental crust. So this is a German drilling project So some of the continental rocks, deep rocks, do have large excesses. Again, and much larger excesses are found in meteorite impacts. So this one is in Canada. Huge xenon enrichment. Tektites are these drops, which are created when you have meteorite impacts. And this one is a lunar meteorite. So since it's arrived on Earth, it has seen some very high pressures and very, very high xenon content. So there seem to be, indeed, some excesses, but to be able to see them, you need to see rocks that have seen high pressure on a small scale or that have been erupted quite quickly. It looks like if you wait on geological timescales, xenon will diffuse out when rocks go back to the surface. But if you manage to bring them up quickly enough, you might preserve xenon excesses. Okay? That's why it's so difficult to find it, because you need to look at rocks that have been brought back to surface condition quickly enough so that xenon didn't diffuse out. So to explore that, let's do some high pressure experiments. So just to give you some ideas, sorry if it's too basic. So we're talking gigapascal scale, 100 GPa, it's 1 million atmosphere. So center of the moon, 5 GPa, center of Mars, 40 GPa, the Earth, almost 400 GPa, Jupiter, another order of magnitude higher, and then the temperature goes up as well. So that's the conditions we need to reproduce in the lab. And there is only one way to reproduce high pressure, is to put a force, as strong force as you can, on as small surface as possible to optimize the force-surface ratio. So you also need to work with very hard materials so that the force is transmitted as much as possible. So there are two types of experiments we've been doing. So we qualify them in terms of sample size. So if the sample size is 1 cubic millimeter, we call it large volume. And for this, we use multi-anvil presses. So this one is a multi-anvil based on the German synchrotron in Hamburg. So you have a big press, hydraulic oil. You have this first stage of anvils here, 6 anvils. And in the cube in between, you put 8 other cubes that are truncated. And in the middle, you put your cell assembly. Okay? So basically, every time you have a nice surface ratio, and at the end you have a huge surface here and a very small in contact with your sample. You can hit that and reproduce high PT conditions, Or you can use a diamond end cell. So diamond end cell, I can hold it in my hand, can travel with it. It's very handy, and you can squeeze samples to all pressures encountered in the Earth, basically, and heat it as well. If you, for example, do laser heating. So it's much smaller, much more versatile. So one of the good things with diamond, except that it's very hard, one of the good things is that it's transparent to a large, frequency range. So it's transparent in the infrared, so you can do infrared spectroscopy, which I will show you here. And obviously you can do, you can have X-rays going through. So you can probe your samples with X-rays. So most of the data I will show you have been collected on synchrotron light sources, especially some in Chicago. We do infrared in Soleil, which is South Paris, and most of the data I'll show you on X-rays were collected at the European synchrotron. So just to highlight what pressure can do. So, of course, pressure first thing pressure does on planetary materials, it compresses the materials. So you have an increase in density. But it's not the only thing. You also induce changes of chemical behavior and of physical properties. So maybe one of the most dramatic change that can happen is metal insulator to metallic transition. So that's one of the, so all of this, oops, it's a little bit blurred, sorry. So all of these images, those are photographs of, you have a diamond end cell, you look at diamond end cell through a binocular with the light from the top. So this is a gasket, usually made of metal, typically uranium. So this imprint, indent you see is the diamond tip with the diamond faces. So that's diamond culate. There is a hole in it, and this shiny hexagon here is a crystal of oxygen. So you have the light from the top. So if you see light shining from this oxygen crystal, it means that it's a metal. That happens above 100 GPa. Oxygen becomes a metal. Inverse can happen. For instance, well, we don't really care in our sciences for this, but still it was very interesting. So in this case, it's sodium. So sodium is a metal. Okay, you squeeze it, becomes black, and then you put the light from below, and you see it's transparent. So in this case, you turn this metallic sodium into an insulator. Usually in planetary science, it's this transition that matters most. The most interesting for us is hydrogen becoming a metal for the giant planet. Well, I'm not talking about that. Xenon also becomes a metal, as a matter of fact. At pressures that we encounter in the Earth core, 150 GPa, it's just the top of the Earth core, and it becomes a metal. So here it was reflectivity measurements, and you see that above 150 GPa, reflectivity goes up. Yeah, so it reflects light, it becomes a metal. So because this was observed, one of the initial thoughts were, well, xenon is in the core, because core is made of iron. If xenon becomes metallic, it can make an alloy with iron. And as a matter of fact, people have synthesized xenon nickel and xenon iron compounds at core pressures, very high pressures. So it's a very interesting chemistry. However, we have to keep in mind that missing xenon occurring both on Earth and Mars. Mars is very small. It's 40 GPa. We certainly don't have metallic xenon there. So no, it's not useful for us. It's interesting chemistry, but that's not what is going to solve the missing xenon problem, because it's too high pressure. We did some xenon water experiment using diamond end cells, and we observed this compound forming. So the yellow sphere is xenon, the red is oxygen, pinkish is hydrogen. So you have this xenon. So it forms at mid-mantle pressures. After this synthesis, others came up with pure xenon oxide using the same technique on diamond end cell, laser heating. So again, it's very interesting chemistry. So it's covalent bonding in all these compounds. It's very interesting, but again, it's too high pressure to explain mass. And the other thing is that in planetary science, you can't have these stoichiometric compounds, because the natural abundance of xenon is much, much smaller than that. So you'll never make stoichiometric compounds with the terrestrial abundance of xenon. Okay, so we need to work with xenon as a trace element. So before that, I've been showing high-pressure xenon chemistry, but xenon chemistry has been known since the 70s. Chemists have been working on that. The first compound was reported by Bartlett. It was a fluoride. These days, you have over 100 xenon compounds that have been synthesized at ambient pressure, most of them at cryogenic temperature. Those are xenon oxides, xenon O4, actually this came in the 70s as well. Xenon O2 is much more recent, so it gives these yellow crystals. The xenon oxides, they are super explosive, so you have to be extremely careful with these materials. That's why they keep them in the ice here. A little bit more stable are xenon perovskite, which are also yellow. Okay, so you have a xenon oxygen covalent bonds in those compounds. So what can we do with xenon as a trace element for planetary materials? So we looked at the most common minerals, which are silicates. So in the mantle, so those are mantle rocks that are brought by volcanism to the surface. So this green mineral, which is the majority of this rock, is olivine, and the building block is the SiO4 unit. So silicon is inside this tetrahedron. The tetrahedra are all disconnected in olivine, and in the continental crust, like this granite, they are mostly composed of quartz and feldspars, in which tetrahedra are all connected to each other. They are all based on this tetrahedra. So we say, okay, let's try to see how xenon behave in those compounds. So I'm not going to show you all the data sets we got, just showing you some infrared spectroscopy using this diamond anvil cell. On both sides, the sample is compressed, and then we slowly hit. So initially, we have the typical infrared spectrum either of olivine here or of quartz here. And when we hit, we observe new vibrational modes in both cases. And when we decrease the temperature, they vanish. So we observe new vibrational mode. We also have Raman spectroscopy indicating that. So we have some proof of interaction of xenon with the SiO2. Very early we suspected there was some silicon release, but the final answer came when we did ab initio calculation with Céline Crépisson. She was a PhD student at the time. So this is quartz structure, this is olivine structure. In both cases, the xenon atom is in yellow, and in both cases it bonds to oxygen atoms, not exactly in the same local configuration, but the bond length is about the same, 2 angstrom, and there is a charge, in this case of almost +3. And this occurs at very low pressures, 1 GPa is enough to induce that. So when you work with xenon as a trace element, somehow you have some chemical pressure, and you can have chemical xenon bonding occurring at much lower pressures than if you just start from pure xenon and pure oxygen. So you can induce this chemistry at much lower conditions. However, this happens at high pressure. If you release the pressure to room pressure, it goes off. The xenon is released of the structure. So next step was to measure isotopes on our samples. So for this, you need to have a little bit more samples. We did large volume experiments. We did olivine, we did feldspars, and we sent the sample to nuclear isotope groups in France. We did observe for the feldspar the orange square, for olivine the green symbols. And if we dope our sample with pure xenon gas, we don't see anything. That's this circle. If we dope the sample with a very diluted gas, with only 1% or 1 per mil xenon in it, then we see the fractionation. And so we have a mass fractionation, okay, of about 2 per mil per atomic mass unit. Okay, so we saw this. So before coming up to some scenario, how to explain it, let's think a little bit about how planets formed. So one key step is this planetary embryos, moon size, Mars size, that probably most of them were molten at some point, got differentiated. And in a magma ocean, the crystals, they always form at some depth. They don't form on the surface. Even the feldspar, they form at some modest pressure. And then because they are lighter, they are less dense, they rise to the surface. But they form at some depth. Same for olivine, forms at depth. And because it's denser, it sinks at the bottom. But they all form at some depth, the minerals. So we say, okay, let's see how xenon behaves when you have crystals and melt. And the literature was extremely controversial on the topic because when you do the experiments at high pressure, you recover your sample. What you observe is something like this. You have a glass, the melt is quenched as a glass, and the crystals, well, you have bubbles. So the empty bubbles are black, and the white bubbles is the SEM, so because xenon is so heavy, it's white. So you see these bubbles, and you don't know what to do with it, because you don't know if the bubbles were all the time there, or if they formed when you release temperature or when you release pressure. So it's very difficult to know what to do with this. So some mass spectroscopists, they thought, okay, let's avoid all the bubbles. And others said, let's assume all the bubbles. So it's very difficult to interpret. So what we did is that we tried to measure that in situ. So we did that in the US synchrotron, where there is a nice press there where you can do diffraction, but it's energy dispersive diffraction, meaning that on this spectra, not only you have diffraction peaks, for example, for the crystals, but if you zoom, this is a zoom here, you also have the fluorescence peaks of xenon. So you have both the Bragg peaks from the crystals and the fluorescence from xenon on the same data set, so, which is nice. And in this case, so the crystals are the black curves, and when you melt, the baseline increases because the melt has some diffuse scattering. Okay, so you know it's molten because you lose the Bragg peaks and you observe this diffuse scattering. So you know where the melt is, you know where the crystals are. You go from this to this by moving your press versus the beam, X-ray beam position. So you can scan your sample, go in the crystal, get your data, then move in the melt and get your data there. So then you focus on the xenon zone and you measure the surface of these peaks and calculate the partition between the melt and the crystal, okay? Just looking at the surface ratio. So first look at the bottom, which was a mix of pyroxene, feldspar, and melt. There is more xenon in the melt than in the crystals, but in the olivine, it was the other way around. In the olivine, that's the initial glass. So we start from a glass, which is doped in xenon, very tiny bit of xenon. We try to put as less as possible because then geochemists tell us, it's not realistic. You don't have parts per trillion, but we need to see something. So we need to put more. But anyway, so that's the best we can do to be able to detect something. So in any case, we start with this glass, we fully melt it, and then we decrease temperature to get equilibrium between the melt and the crystals. And in that case, we couldn't even detect the xenon in the melt. Okay, so we had to recover it and do some mass spectroscopy on the glass. Obviously, xenon was very efficiently sucked by the olivine out of the melt. So let's try to put all the puzzle pieces together. In the crystalline silicates, we have xenon substitution to silicon atoms bonding to oxygen. That's what ab initio calculations tell us. We observe mass-dependent fractionation of xenon on our recovered sample. Not for all crystal melt systems, but for some of them, and in particular for olivine, we have trapping of xenon in the crystal at equilibrium will melt. So that's experimental, and now the observation, strong depletion in light isotopes, and same problem, same xenon depletion for the Earth and Mars. Last thing, this strong depletion in light isotopes has changed, is recorded differently throughout the Earth history. Okay, so how we reconcile this together? Well, that's the scenario we came to. So you have these starting planetary embryos that are molten. Crystals form at depth, they trap xenon, and they trap the heavy isotopes. The light isotopes are preferentially released, get somehow into the atmosphere, and then you have a system, an early solar system with lots of collisions between these bodies. Each time you have collisions, you lose the atmosphere. So you lose this light xenon isotope fraction. And if you repeat this about 10 times, then we can explain these numbers in terms of isotopic fractionation. Yeah. So collision, about 10,000 collision between planetary embryos is actually consistent with modeling of planetary system formation. And in the case of the Earth, at some point, the system becomes closed. So because we have exactly the same xenon depletion in Earth and Mars, we think that the system becomes closed when the planet becomes Mars size, reaches Mars size. Somehow then it's heavy enough to retain its atmosphere, and the system becomes closed. Yeah, so basically that's the story. Yeah, and then subduction kicks in, and continental crust kicks in, and you probably have a release from the trapped xenon that makes the isotopic evolution of the atmosphere that is recorded. That's the Earth science side of the story. So most of the time, as I said, so this is SEM image of feldspar doped with xenon. So most of the time we see these bubbles. Okay, I kept telling you about these bubbles, but not all the time. Sometimes the xenon is in homogeneous phases. So we saw like this one, and in this one as well, we have a nice octahedra. Sometimes we have 2-8% xenon. So I say, well, maybe on a material point of view, that could be interesting to come up with xenon-doped materials that are stable at room conditions. So we tried to work on that. So those are X-ray diffraction 2D data we got in situ at high pressure and temperature. So we have a glass, we compress the glass, we heat it, and then it recrystallises at some point when we heat it. So that's typically the kind of data we get at a few GPa when we have feldspar recrystallizing. Accidentally, we went to a bit too high pressure. We overpressurized the sample. And in which case, we got this beautiful X-ray powder diffraction pattern. So we said, okay, well, what's this? So this turns out to be what is called simrite. I don't know if you ever heard about simrite. Anyway, me neither before. So it's hydrosanidine. You actually can get it in subduction zones from the coastal continent. Okay, if you have siliceous-rich sediments, they can turn into this simrite. So, well, that's interesting. So this simrite, it has this structure. It's a layered structure. It's a high-pressure phase. So these purple spheres are potassium atoms. They are highly coordinated because it's a high-pressure phase, so there's 12 oxygen atoms around it. It has some water in the cages, so it phyllosilicates, so it's layered, and it has cages with water in it. So we say, well, okay, it makes sense. It's a layered structure. It has cages, so of course xenon can stay in it. Either between the layers or in the cages, it has plenty of space to stay there. However, it turns out it's not the case. So we took this sample to the European synchrotron, and this we measured in last November. So this is X-ray absorption spectroscopy, where you basically scan the next neighbors around your element. So it's a chemically sensitive probe. You only get the first shell or first two shells of atoms around the atom you're probing. So we are at the xenon edge. So that's a freestanding sample, no pressure, no high temperature, nothing. And you see this signal here. So when you do X-ray absorption spectroscopy, when you see a distance here, it's not the real distance. Yeah, it's not like X-ray diffraction. In X-ray diffraction, you fit a distance. It is the real distance, not X-ray absorption spectroscopy, because it depends on the path, the exact path followed by the X-rays in your sample, and there can be multiple paths. So it's more complex than that, and you need to have some starting model structure to fit it. Okay, so I won't go into the details, but if we try to fit this data with just one shell of atoms, and the best fit we got for xenon oxygen, in which case you get 3.2 angstrom, and what I haven't shown here is that the xenon edge is shifted in this compound compared to xenon gas. We had a standard here. During the experiments, we had xenon gas as a standard, and there was a shift of the energy, which tells you that there is a redox change. Okay, so we have this distance, 3.2 angstrom, so it's much larger than what I've shown you before in quartz and olivine, where it was 2 angstrom. That's much larger. Yeah, so it's a certainly weaker interaction. It's there, but it's weaker. And so I'm not going to show you, but we also can process this nice powder quality X-ray diffraction data, and basically the only possibility is that xenon goes into the potassium atoms, and this gives you this distance between potassium and oxygen is 3.2 angstrom. Yeah, and actually the second peak here, which I haven't tried to fit in this figure, but this second peak is the next one, the next potassium that you see. Yeah. So it looks like here it's not xenon to silicon, it's xenon to potassium substitution that we have. Yeah, and this is stable back to room condition. We also try to reheat that, and we have been reheating it to 500 C. It's still there. The bond is still there. So we'll see what if there are some material science perspectives trying to dig into that. But it's also interesting for earth sciences because when the sediments go back on top of the lithosphere, back to the mantle, these sediments can be very silica-rich, in which case you can form this potassium seamoide. But even in the basic crust, you can have some high-pressure potassium silicates, such as phengite, and potentially, it remains to be seen, but all these phases potentially could carry back xenon, along with water, along with halogen. So this figure I stole from this recent paper where they explored phengite stability field, which is quite high, actually. And phengite can carry lots of things. And in this paper, they were interested into halogens. But that's potentially, these phases are potential carriers of xenon back into the mantle. Okay, so going on to argon. So there was this science editorial with no references. So Philip Abelson, I think he discovered neptunium, but he also was at some point the director of the geophysical lab. It's where I started working on xenon at the Carnegie Institution of Washington. So maybe because he was director of the geophysical lab, people at the time were trying to do some experiments. I have no idea. He doesn't cite anyone in his editorial. But he mentioned that at high pressure, chemical reactions are seen that do not occur under ambient conditions. Argon reacts with hydrogen to form argon H4 and with oxygen to form argon O6. So I don't know. I don't know where this comes from, but that's the science editorial from 1999. Okay, as a matter of fact, there are very, very few argon compounds made up in chemistry. There are some, and there are some argon fluorides or even argon silicon bond, I think, was made up recently. At high pressure, this is the only material that has been synthesized so far in diamond and cell, argon nickel. A few others have been predicted ab initio calculations, quite high pressures. In all three cases, there are no oxides. Yeah, so far, really no oxides, whatever the conditions found. It's more the other way around. Argon gains electron, doesn't want to give electrons, looks like. Then there was this paper from the Bayerische Geo Institute in 2020. Those are large volume press experiments, and they squeezed silicates. They have reached the Bridgmanite field. So Bridgmanite is the lower mantle phase, and the basic unit here is not SiO4 anymore, but it's SiO6. So silicon sits into an octahedral site bonded to 6 oxygens. And in this phase, they measured up to 108% argon. So a lot of argon in this phase. Maybe the guy was right. Maybe you can make some argon O6. So before going straight to Bridgmanite, decided to go slowly, as we did for xenon, and start with the SiO2. Let's see what happens when we squeeze argon with SiO2. So the SiO2 phase, which has silicon in octahedral sites, is dischovite. On multi-angle presses, experiments recovered the sample. And in a few cases, we did observe argon. So that's an SEM image. So where it's blue, it's argon. So in some cases, we put also aluminum, thinking that maybe that would make some balance, charge balance. Anyway, so we see that most of the sample has no argon at all, but there are some locations, and those are not bubbles. You have some locations where you do have quite a lot of argon in there. Initially, I thought it was all stishovite, because when I first looked with Raman in the lab, it was stishovite. So we have Raman spectroscopy data, and interestingly, in this coesite mixed stishovite sample, the coesite peaks are a little bit shifted compared to room pressure coesite. Depending on where you look at, it's 1 to a few GPa. So I don't know if it's a chemical pressure, or if the coesite is an inclusion in the stishovite. that needs to be looked at. I'm not sure yet. And we also have infrared data. So those are infrared spectroscopy, both in situ at high pressures and temperature and ex situ done in Soleil. So basically, you have the cold sample, and then we heat up to 1200, basically 1000 C, and then we recover. So it's very different from xenon. In this case, so all these peaks here, they are just normal coesite, but in this zone, you have little bumps that becomes much clearer when you heat up, but I think they are there all the way, in fact. It's a bit, you see them better maybe in the in the freestanding sample. So you have these oscillations here of peaks that are not here when you don't have argon. Okay, all the other peaks are the same. But in this area, you clearly have 3 new vibrational modes. They are always there. They are there at high pressure temperature. They are there when you quench it. So what's the geological side of it? I'm just starting to dig into it. So it's very interesting because when I was a student in Paris, my first field trip with my mentor was Christian Chopin, who is this guy. So Christian discovered coesite in the Alps. So coesite is one of the high pressure phase of silica, which was a remnant of continental crust being subducted. I mean, at above 100 kilometers. You know? So he found this in the Alps, and he discovered it in 1984. So it's quite late because the Alps have obviously seen a lot of geologists for a long time. But why it was so difficult is because it's not an outstanding outcrop. So this is Doramera, so it's just gentle hills, lots of bushes, everything. So everything was hidden. There was no massive outcrop, no, you see. But he found it. He found it, so this is the rock. So it looks like sugar, because the coesite, when it transforms back to quartz, it looks like sugar. And the pinkish areas are garnets. And within these garnets, you have remnants of coesite that has not transformed back fully to quartz. And that's how he discovered it. So I went with him with, not in 1984, I'm old, but not that old. So I went with him, collected some rocks, did something at the time as a student. So for me, it's actually, I'm very happy to come back to him. And we were very pleased to discuss again together. Very interestingly, when these rocks, so you have also shiny minerals, which are the potassium-rich micas, where you can date them with the potassium-argon dating method. Yeah. And when people were trying to put an age on these rocks, looking at these micas, they were finding over 600 million years age for these rocks, which is obviously very wrong for the Alps, which are way younger, only 35 million years. So there was something wrong. So there is this excess of argon, and it's actually worldwide in all these ultra-high pressure rocks, this excess of argon. Nobody knows where it comes from. Yeah. So we might have the start of an answer for it. Yeah. So coming back to noble gases tracing Earth atmosphere evolution, argon isotopes are also widely used because, again, argon is assumed to be a volatile element degassing to the atmosphere. So if you look at that, you can come up with models of atmosphere formation, but also you can constrain a continental crust formation. So I'm not showing you, I'm showing you just one of the most recent model by Shen et al. Last year, trying to be consistent with the mantle dynamic evolution models. So the cooling of the mantle over time, which is the orange data set, trying to fit with the present day 40 argon content in the atmosphere, 36 argon in the atmosphere, and trying to fit with the 40-36 argon ratio in the mantle, trying to explain all this with these models, and also trying to fit these 3 points, which is actually just one. So this is measurements of argon isotopes in fluids, in fluid inclusions in quartz that are interpreted as paleoatmosphere. Okay, and it's very difficult to date. So it's only one data point, but they are not sure of the age. Hence the 3 points, yeah, as far as I understand. Okay, so they try to fit that, and the conclusion is that you have a very early massive degassing of the mantle here. And the other conclusion is that to explain the amount of argon-40, you do need, mantle degassing is not enough. You need to have the continental crust kicking in. Otherwise, you don't explain it. You miss something. Okay, so very early massive degassing of the mantle and very early growth of the continental crust. When I was trying to see who cited this paper, I came up, this continental crust paper, I came up on this very interesting paper when they reinvestigate the fluid inclusions in minerals. So this was, those fluid inclusions are square because they are in halite, which is cubic. Yeah. Cubic crystallographic structure. So they analyzed this fluid, and in this paper they describe very well that when you measure noble gases content in there, they are not direct reflection of atmosphere, because you need to take into account the different solubility of the gases, and they need to correct for this effect. So they said that when you have these measurements in fluid inclusion, they're actually just an upper limit. So they didn't correct the previous data set, but the data set they got on this sample, which is 800 million years old, is something that is here, so much lower than the curves that passes through these old points and the current atmosphere. Okay, they get something much lower, and very interestingly, these fluid inclusions have much lower argon content and much lower oxygen content. For oxygen, it won't surprise you, because 800 million years, it's when the oxygen rise in the atmosphere. It's just the snowball Earth event, so it's the second oxygen rise in the atmosphere. But it looks like it's correlated with the argon. That's the interesting bit. So in that case, this could be revised down, so that it goes through this point, and then there should be some massive degassing of argon to go up to the current level. So I'm not sure what we're going to say about that, but I was looking at about crustal thickness, because coesite is stable only at quite high pressure in the crust. You need a thick crust to have coesite stable. So I was trying to look at the evolution of crustal thickness, and it seems super controversial. So here you have two papers telling you exactly the opposite. You know? So on this one, the crust was the thickest at 1 million years, and here the crust was the thinnest 1 million years. Maybe some of you have a much better insight than me on these curves. But I hope that maybe if we manage to understand argon in coesite, obviously this to me would make more sense, because if you come up with a very thick crust that could store argon, because it's very thick, more high pressure domains. And this is the period where you had a supercontinent. So this origins. So it makes sense to have lots of origins and deep crust. Then when you break it, you release everything. I mean, you release a lot of argon because you thin it. But we need to dig into this. So I'm just ending the talk with some helium. I haven't done anything on helium, but just to show you some nice data, I think. So there are helium compounds that are predicted. None of them is covalent. It's only ionic compounds, because helium is stabilizing ionic compounds. And so those are with planetary materials. Of course, there are much more high-pressure helium compounds. I'm just showing you those who could be relevant for planets. So with the water, with NH3, with FeO, you have these compounds forming. More recently, the Japanese group synthesized using diamond and gold cell this iron helium compound, which can store a lot of helium. So this is diamond and gold cell experiments, so they have X-ray diffraction data. That's how they came up with these structures. But very interestingly, they recovered the sample from the diamond and gold cell, and they measured the helium content. They did it first at room temperature, didn't see anything. And then they did it cryogenically, and they measured a lot of helium in there. So you need to, helium remains in the iron, but you need to be very careful when you measure the helium content. If you don't measure it at cryogenic conditions, you won't see it. It will go away. Yeah. So basically they say, okay, well, iron cores are very likely strong helium reservoirs. That's their conclusion. And I was showing that in February to students in a winter school on exoplanets. And then, because in exoplanets they are used to look at the observatory data, one people in the assistants were, oh, do you know this paper when they observed the planetesimal being disrupted and went into the star and blown up? Well, no. So here are the data sets. So that's from the Mauna Kea infrared telescope facility. So they have various years, and they observed the iron line here. So bear with me, I'm really not familiar with this kind of data, so just trying to explain a little bit. So you have several years, so you can see that the signal diminishes with time, so it happened and then you lose the signal, so it's not something, it's really something that lasts just a few years. And then you don't have just one band, it's split, because this is the blue shift and this is the red shift. So it tells you that you have jets of gas going into the opposite directions. So it's not the star you're looking at. It's something else that crashed into the star, basically. So this is iron, so it's basically the core of it. So there is sulfur lines, there are silicon lines. Those are two potentially siderophile elements that go in planetary cores, fair enough. And then there is the helium. There is huge helium peak in there. Okay, there is hydrogen too, but hydrogen is not, you don't have this blue shift and red shift, so it's the star. But helium, you do have this blue shift, red shift, and you do see it disappearing with time. And at the time, the authors say, well, we don't understand where it comes from. It's very consistent with what the Japanese have seen in their high-pressure experiments. So maybe experiments will become useless in some time. We just look at what the observatory tell us about planetary composition. It seems very promising. Yeah, at least it's very impressive. So yes, that's the story. So they have this, the flow of this, when the planetesimal gets disrupted and then into the star. Okay, so my conclusion is that if we enlarge to other planets, like the giant planets, noble gases are also widely used to understand either interior processes or to understand where the materials come from to build up the giant planets. And you still see this kind of sentences in the papers. You do that because noble gases are chemically inert, not condensable, and uniform all over the planet. So I do hope I convinced you that is not the case. They are, of course, very useful traces, but you need to consider that they are not chemically inert at planetary conditions. And thank you very much for your attention.